Hey, Jason. We miss you. All right, they are ready to get after it. They're like begging me to start the notes. So fine, you guys will start.
I'm gonna watch this on Monday before class.
Okay.
How was your break, Jason?
How's Florida?
How was Florida? He's already back.
As a refresher, here I'll give like a 1 minute refresher for you guys just to like sit back and relax. Okay. We are talking about finding the area between two curves. So basically, we just find the area under one of the curves. Where's that slide I'm looking for? This one. We find the area under the top curve. And then we subtract out the area under the bottom curve. So we subtract that out and then give us the area between the two curves. So it's always top minus bottom. That's what you need to know when we're doing this with respect to x. And what that means is when I draw in little rectangular strips, I have this on this slide, yep, rectangular strips. If I'm really finding the height of these, I can just figure out what the top of my curve is minus the bottom. The width we call dx, and then to add up all that total area, we use our integrating techniques. So top minus bottom, that was our big idea. Okay, we did a few examples. And I think we even did one in our calculator too. Oh yeah, we did that kind of like right at the end. So here's an example, a couple examples of some curves where your top and your bottom might like switch when you're integrating over a certain bound. Okay, so let's try this one. It says find the area of the region in the first quadrant that's bounded above by y equals the square root of x and bounded below by the x-axis and the line y equals x minus 2. Okay, those are nice, easy parent function of our square root, linear function, nice, easy things to graph functions. Okay, I should probably go down here. So let's do my square root curve first. We got 0, 0, we got 1, 1, we got 4, 2. All right, there's that curve. I'm actually going to do it in red. Then we have the line y equals x minus 2, so that's a y-intercept of negative 2, slope of up 1 over 1. So they should intersect at 4, 2. We should check that algebraically. So remember, that's kind of like the first thing before I start integrating is I find the intersection points. And sometimes students like to find the intersection points before they graph it, just to give them like a little visual of like, okay, here's where they should be crossing, which that's fine too. I usually like sketch what I can, and then if it's unclear what the intersection points are, I check algebraically, but like I said, you should always make sure. So remember, to find the intersection points, you just set those two equations equal to each other and solve for x. So here I'd have to square both sides. So these would intersect at 4. X equals 4 and x equals 1. Now, if you're like, well, what the heck, when x equals 1, these don't intersect. And if you remember back in like your Algebra 2 days, when you're solving equations with radicals, specifically square roots, sometimes when I square variables, it creates extraneous solutions. So if you were to go back and plug 1 in here, the square root of 1 is 1. 1 minus 2 is negative 1, so this is actually an extraneous solution here. Remember that? Good times. That happens when you square an unknown. When you square a variable, often it introduces extraneous solutions. We just did this too. Like even in pre-calc, when you're solving that trig equation, sometimes you have to like square both sides and check for extraneous solutions. But all right, so we know they should intersect when x is 4, right here. So my graph makes sense. So it says find the area that's bounded above by my red curve, bounded below by the x-axis, and the line y equals x minus 2. So we're finding this area right here. So let's go pink. Okay. So if you draw in your vertical strip and you're like visualizing what the height of that strip or that rectangle is, you'll notice it's dependent on where you draw that. If I draw it here, the height of that would be the red curve minus 0, where the x-axis is. But if I draw a strip right here, you're like, well, now the height of that is not the red curve minus 0, it's the red curve minus the blue curve. Okay, so it's an example of like when our boundaries are changing here, when our top minus bottom might switch. So what we'll have to do is we'll just kind of separate this. We can see it crosses my y-axis at 2, and that's when it switches over. So we'll just have to integrate this piece, and since area is additive, then we'll just add in that piece. Okay, so let's actually color coordinate these two different colors. Let's do this one orange. So I'll do the pink one first. So the area of the pink would be, now since I'm doing vertical with respect to x, I'm going for my bounds along the x-axis. So from 0 to 2. Top, which is the square root of x, minus bottom, which is 0. Technically, you don't need that minus 0 because we know if we just integrate the plain old square root of x, that's doing the area under the curve of the square root of x to the x-axis. So technically, you don't need that, but it's good to see the top minus bottom here. Top minus bottom. Plus, the orange area would be from 2 to 4, since that's where they intersect is at 4. From 2 to 4, top, square root of x, minus the bottom is now x minus 2. And when you're minusing that, make sure to put it in parentheses. Dx. Top minus bottom. Okay. I just got to clean this up a little bit, and we're ready to use our calculus integration tools. So here, square root of x minus 0 is obviously just square root of x. I'm going to rewrite it as a power. Orange. Let's go x to the 1/2 minus x plus 2 dx. This is looking good. Let's just go ahead and find our antiderivatives, and then I'll give you the answer here. All right. Add 1 to the powers, 3/2, divide by 3/2, or times by 2/3. Plug in bounds of 2 minus plugging in 0. Plus. Same thing, antiderivative, 2/3, x to the 3/2, minus 1/2 x squared, plus 2x, plugging in 4, plugging in 2. All right, you go through fundamental theorem of calculus, plugging in 2, your upper bound, minusing plugging in your lower bound, plugging in your upper bound 4, minus plugging in your lower bound 2. I got 10/3. What was this? 10/3 for that area. So if you wanted to check this in your calculator, you would have to set up 2 separate integrals, just like we did. Okay, we'll do one more like this, where the bounds, the top and bottom kind of switch, and then we'll look at some with respect to y. Find the area of the region enclosed by the graphs of f of x equals 3x cubed minus x squared minus 10x, and g of x negative x squared plus 2x. Okay. So this one might be a good idea to kind of figure out where they intersect first. So you have a general idea of what this cubic function looks like. It's a positive leading coefficient. It's gonna look something like this. And I have a general idea of my g of x is a sad face parabola. It's gonna look something like this. But if we can find where they intersect first, that might help us graphing it because I don't know exact points. You have strategies to graph these. You could like complete the square with this one if you wanted to, or you could do like your x equals negative b over 2a to find the vertex. Okay. Usually our strategies for graphing like higher degree polynomial functions when they're in standard form is like find the end behavior and just kind of like plug in some points really. Sometimes you can find like x and y intercepts to help graph them, but we're not in algebra 2 anymore. We're more concerned about the calculus piece of this. So let's go ahead and see where they intersect. Oh, we're going to do first 3x cubed minus x squared. Again, if you're asked to find the intersection points and you can't solve it algebraically or it's not like a nice clean number, you'd be able to use your calculator to do that. I have one in here that we'll have to do that for. All right, set this equal to 0. We can factor out a 3x. So these intersect at 0 and positive and negative 2. Difference of squares. Or you can just set x squared minus 4 equal to 0. I'll show one more step there. I like to factor. Okay. So when I'm drawing my sketch, I know they intersect at positive, negative 2, and 0 for their x values. So you don't have to really have, honestly, like a perfect sketch of these. Maybe find like one point to make it more accurate. We can also graph either a graph or two. Let's just quick see what this cubic one looks like. So we got 3x cubed minus x squared minus 10x. Let's just get a little visual. That one's going to obviously go through the origin. All right, so it obviously goes like really high, really low. You don't need to graph it super accurately. So it's, I don't think it's crossing at negative 2 though. Looks like just to the left. Let's see, when x is negative 2. Have I shown you guys that before, that tool? Okay. When x is negative 2, it's all the way down there at negative 8. Okay. So again, we don't have to be super accurate if you wanted to do this. You can negative 8 crosses at the origin. Let's figure out where it is. And again, you could do this. If you didn't have your graphing calculator, you would just have to like make a table. You could plug them in yourself by hand, but just to save time. For the most part, if you're given one without a calculator, it's going to be something easy you can graph, kind of like the last one. All right, what about when x is 2? That does not look right. Is that 0?
Check your window.
Oh, maybe my window's in terms of pi. Ooh, good call. I was like, that does not look like it's crossing at 2. Thank you. That's good. Oh, and my y-axis was also not very scaled. We could go negative 10 to 10. There we go. That looks better.
Is your scaling
Let's try this again. X is 2. What the heck? Oh, my scale. You're right. That is bonkers. My y scale's fine. Okay, there you go. Now it makes more sense. I don't know how that got messed up.
We did wrong with sine and cosine.
And I changed it to that. That makes sense.
Like our windows.
I also, in pre-calc, we use that a lot. All right, so go something like this. No, it dips below. Something like that. Again, we don't even really need to know this. You can mark it if you want, but. So same thing with my parabola. But you already know 3 points on this parabola. You know it's a sad face. You know they intersect at these points. And you also know it's going to go through the origin. So without even doing like any of the completing square, calculating the vertex, we know it's going to look something kind of like this. But in this case, we don't need to know exactly how high or how low because we're doing this in terms of x. And so our bounds are not going to depend on like how high or how low this goes. We're going to find this area, which if you look at that area or if you draw your rectangle anywhere within here, you'll see your height of that strip. The top minus the bottom would be the blue minus the red, even if you drew it like way over here in that region. And then if I look at this other region, I notice that my top and bottom curve switch. Or if I draw a rectangle here, the height of that rectangle would be the red minus the blue. So again, we're going to have to set up 2 separate integrals for this. So let's go with the green one first. All right, so that's going to be where they intersect. Again, we're doing this with respect to x, in terms of x. From -2 to 0. We got our top, which is our blue. That's our cubic one. Minus the bottom, which is the parabola.
Pardon the interruption. Katie Brown, is for the counselor. Katie Brown.
Move this up so I have more room here. Okay. There is the first section. So just like the last one, I'm gonna have to add in plus okay. Plus of my orange from 0 to 2. This time my top. And obviously the order matters because we're subtracting. That's why I set up 2. Minus bottom. All right. So we got top minus bottom, top minus bottom. All right. Clean it up a little bit, and then we'll do the fun part, the integrating. All right, so I got 3x cubed minus x squared plus x squared, no more x squareds. Negative 10x minus 2x would be minus 12x. Careful with your subtraction. Make sure you put those bottom ones in parentheses, the ones you're subtracting. Plus 0 to 2. Negative 3x cubed. X squareds cancel again. 2x plus 10x is plus 12x. Okay. Antiderivatives. This would be 3/4 x to the 4th minus 6x squared similar, negative 3/4. Okay. We end up getting a final answer of 24. Which that big number makes sense. I mean, our graph went all the way down to like -8, and the peaks of the cubic one were pretty high. As always, you can check in your calculator. I'll do that quick. Let me just plug in this one to Y2. Just as one last reminder of how to plug these in because it's important. Math 9. All right, so my first one was from -2 to 0. My top was my blue curve, so I have that in my Y1 minus my Y2, top minus bottom, with respect to X, plus Math 9, 0 to 2. This time my top was the parabola, the red curve, top minus bottom, dx. 24! Okay. That's pretty much it. Sometimes maybe the functions will get like a little more complicated. I know we kind of did like a lot of polynomial ones, but we did a trig one in there. Didn't we? Maybe not. Did we not do a trig one? Oh, I think I was just doing one. I have one later on in the notes. I think that was one I was just doing. This one that I was just doing. Yes. Okay. But top minus bottom. And there's some too in the homework, I think, where it just says like use your graphing calculator to integrate it, where you don't have to do it by hand. So just make sure you're like following those directions. What if our region that we're trying to find the area looks something like this? And if I were to try to draw a vertical strip in here, don't do this, but if I were to draw a vertical strip, you're like, the top of that curve is the green one. But then if I draw it over here, now the top is the red. So how can I do a top minus bottom in this type of situation? And you might think, all right, well, instead of drawing vertical strips, you'll notice if I were to draw horizontal strips, that's what this is. Wait, no, that's not what I want. This. Aha. Horizontal strips, that we could have a top minus bottom type of situation. I'll draw it in. Or not a top minus bottom, I should say a right minus left type of situation here. Okay, I'll show you what I mean. I don't know where my pen is. I want to use black. There we go. So basically, this question asks, do we always have to integrate with respect to y? And sometimes our equations are like given to us like this, like explicitly solved for x. So like in terms of y. So do we always have to integrate with respect to x? The answer is no, especially in this type of situation, we can integrate with respect to y. So if you draw a horizontal strip, you'll see that we could find like the height, if I'm looking at it sideways, I can still find the height of these by doing the green curve minus the red curve. And we're just going to call our width now dy. This is now our width. So we're going to integrate these with respect to y. Okay, here's what I want you to write down. I'll write this down. So basically, I always integrate with respect to x unless my curve is in terms of y, or when I sketch the shaded region, I notice I have to use like horizontal strips in order to find the area. And sometimes you can do either or, but usually we're just so used to doing things in terms of x that that's the route that's more comfortable for students. I think I even put a problem in here where we're going to do it both ways. We're going to integrate with respect to x and with respect to y, and you'll see obviously we'll get the same area. But when this type of area is presented, to integrate this with respect to y, we now look at the y value for our lower bound. Let me just call that a. And the b value, meaning the y value of our upper bound. And instead of doing top minus bottom, we're going to do right minus left. because that's really, if you were to turn your paper sideways, you're going to flip it. That's really just top minus bottom oriented in a different direction. But we're doing this now dy with respect to y. Okay, so here's kind of like the textbook definition to find the area with respect to y. It's still from some interval a to b. What confuses students is they still always want to use like the x bound, but if you're doing it with respect to y, you gotta have to look like your lowest y value, your highest y value for your bounds. And then in this case, let's go, our top was f of y. So some function that's in terms of y minus the left, which is g of y, dy. So these are definitely not as common, but definitely something you need to know for the AP exam if you have to integrate with respect to y. Okay. Let's try a couple of these. Let's really try to get through all of those. So it says find the area enclosed by the graph of x equals 10 minus y squared and x equals 1. The only thing also I should add this in, your graphing calculator can only integrate with respect to x. So there's no like settings to change it, unfortunately, with respect to y. Similarly, like your graphing calculator can't graph this because when you go to your y1, all you have is y equals, and you like can't change that to x equals. Your calculator can only do it explicitly when it's solved for y. So when you're sketching these, I mean, this one you know what this looks like. X equals 1 is a vertical line. But this one you might not know what that looks like. So go ahead and like solve it for y algebraically to give you an idea of what this graph looks like. All right, I'm going to do that right here. So I'm going to add over the y squared and subtract over the x, square root both sides. And I get y equals plus or minus the square root of 10 minus x. Now, just to give you a visual, you can plug this in your grapher if you're ever not sure what this looks like. You just have to do it as two separate ones. So you got to do the square root of 10 minus x. There's my positive. Oops. There's my positive version. And then you'd have to do, put the x in there. There you go. And then you'd have to do negative square root of 10 minus x. So you know what like a square root curve looks like. All right, so the negative is just like a reflection. And it's just basically like a sideways parabola is what it looks like. Oh my goodness. Struggling today. Something like that. But here's, I mean, you could also know this. You know, you guys do a little bit of transformations in pre-calc. I think I'm going to hit it harder next year. But there's also a couple of transformations here. This is a shift to the right 10. This is a shift to the right 10, and it's a reflection. So that's why it's oriented this way. This way instead of this way. So it got reflected and it got shifted to the right 10. So here's the positive, and then the negative gets reflected over the x-axis. So here's the negative. Okay, so let's just sketch that. I'm definitely not going to, I'm just going to call this 10. I'm going to draw 10 dash marks, 10 tick marks, whatever you want to call it. All right, I'll do this one in blue. So this is all one function, looks something like this. So there's that curve. And then we have the curve x equals 1. So that's this vertical line. Okay. So you can see our area that's enclosed here. It's going to be all of this. And if I were to try and draw a vertical strip, I was like, I have my whole curve is my top minus bottom. So in this case, if I draw a horizontal strip, I can just do my right minus left, my blue curve minus my red curve. Again, if you were to like look this up, it's still your top minus bottom, just doing it in a different direction. Okay, so what you have to be careful of is this is not the integral from 1 to 10. Because that would be with respect to x. We have to do with respect to y. So we got to figure out where these intersect here. So to find my bounds, I need to find how low my graph goes in terms of y and how high it goes in terms of y. So I need to know when 10 minus y squared equals 1 is where those would intersect. So that's at positive negative 3, right? 9 equals y squared. Yeah. So negative 3 and 3. What were you saying, Mark? Would it be easier to do that?
Couldn't you just solve that x equals 10 minus y squared and just say x is 0? Because that's when it would intersect the y-axis.
Oh,
But your way is way easier.
okay. I see what I think I saw what you're talking about though. Just like always, to find where they intersect. And if you want to do that like first, sometimes people like, I like to like know how high or how low to go, whatever. Set them equal to each other, and just remember this is in terms of y, and that's okay because that's the numbers we want. We want to know where they intersect in terms of y because that's going to give us our bounds. Sometimes people will solve this and then they think they intersect at positive negative 3 on the x-axis, and I'm like, whoa, those are in terms of y. All right, so to find this area, we would go from negative 3 to 3. We're doing this with respect to y. Negative 3 to 3. Right minus left. So 10 minus y squared. We're doing it with respect to y, so all your equations should be in terms of y. Minus 1. Right minus left. And this is just the equation x equals 1. I guess that's technically not in terms of y, but you get it. Right minus left. And then this would be dy. Careful here too. I should point this out. Technically, this is more just like transformations in general. Technically, like some students are like, oh, it's plus 10. Isn't that a shift to the left? But technically, like, there's your reflection and there's your shift right 10. That's how it would normally like look when you do these with transformations. They kind of like leave in that form so you can see the separate transformations. But anyways, if you have a grapher, you can tell that. I just saw that on my paper, so I remind you. Okay, let's clean this up. So I'd probably do negative y squared plus 9. Antiderivative, negative 1/3 y cubed plus 9y. Here's the good news though. If you type these in your calculator like in terms of x and you integrate this, it will still calculate the right area. Okay, you just have to change everything in terms of like just you're using essentially the dummy variable of x to replace the y. It can still calculate that. It just can't like graph it. I got 36 for final answer. We better try one more. Or do you not? Or you guys want to stop? Okay, that's fine. We can stop. It's Friday before spring break. You're right. I made you do a lot. What'd you say?
Did you make us do a lot?
No, I don't think so. You feel like that?